So next up is three-phase full converter, and this is the diagram of three-phase full converter. It resembles the single-phase full converter bridge construction, but it has another extra leg. So again, for this case we are using a resistive load, so this freewheeling diode is unnecessary, and as opposed to the previous diagram, this lower portion contains thyristors. So we need to trigger all of these thyristors to get a conduction. So this triggering is a little bit complicated as compared to the previous circuits, but if you follow the pattern it will become easier. And again, as no terminals of the load is connected to the neutral, we will have to rely on the line voltage for these types of circuits. So in this circuit, maintaining the triggering sequence is really important because this triggering is a little bit complex. So in this case, at alpha equals 0 with respect to this crossover point, we need to trigger the T1 right at the moment of this crossover point, or alpha equals 0. So here again I have changed the orders of these thyristors. I think this is easy to remember: T1, T2, T3, 4, 5 and 6, as opposed to the book where it will be a little complicated to remember. So T1, T2, T3, T5, this is a bit complex, so I have rearranged this in a very simple chronological order, which is T1, T2, T3, 4, 5, 6. If you don't like it, you can always follow the diagram drawn in the book, which is a little bit complicated in my opinion. So in order to change the chronology, we have to change the triggerings as well, but these changes are easy to remember. So first thing first, we have to trigger T1 at the desired alpha. So in this case, it's been triggered at alpha equals 0 with respect to this crossover point. So T1 is triggered at this point. So for the time being, forget this portion of the T1 and forget the other repeating pulses. We will be discussing it in a moment. So after 120 degree of 4 blocks of T1, T2 will be triggered. So the gap between T1 and T2 is 4 blocks. It is depicted here clearly. So 1, 2, 3, 4. So T1 to T2 is 120 degree gap. Again, from T2 to T3 there will be another 120 degree gap. So from T2 to T3 here is a gap of 1, 2, 3, 4, 4 blocks of 120 degree. So this is easy, just like the previous circuit. T1, T2 and T3 is 120 degree apart, or 4 blocks apart. So T1, T2 and T3 remains the same as the previous circuits. So here comes the tricky part: T4, T5 and T6. So what is the separation between T4 and T1? T1 is triggered when A is highest and T4 is triggered when A is lowest. So the separation of T1 and T4 must be a half cycle or 180 degree. So after 180 degree of triggering T1, we need to trigger T4. So this gap must be 180 degree or 6 blocks. So here you can see T1 to T4 gap is 1, 2, 3, 4, 5, 6, 6 blocks. So the separation of T1 to T4 is 180 degree. So same thing will happen to T2 and T5. They should be separated by 180 degree as well. So from T2 to T5 we have 1, 2, 3, 4, 5, 6 or 180 degree gap. So for T3 and T6 there will be a 180 degree gap as well. So if you can draw the triggering the right way, the output will be much easier to draw. Here 2.5 cycle is drawn, but you only need to draw it from 0 to twice pi or this gridded portion. You don't need to draw this portion or this portion, and the crossover point will be just on the pi by 6 line. So the triggering will have to repeat after every 60 degree, otherwise there will be no conduction. So T1 will repeat after 2 blocks. So same goes for T4, T2, T5, T3 and T6. So to sum up the triggering, T1, T2 and T3 will be spaced by 120 degree, and T1, T4, T2, T5, T3, T6 will be spaced by 180 degree, and every pulse will be repeated after every 60 degree. So that's the way a full wave control rectifier or full converter is triggered. So if we are done with the triggering, we will start drawing the output waveforms. So just in this very moment T4 and T2 is on. So if T4 and T2 is on, the current will start from B through T2 through load through T4 to A. So the load voltage will become VBA. So this portion of the output waveform will be copied directly from the flipped version of VAB. In this portion T4 and T3 is on. So for T4 and T3 we will have VCA. So this portion of VCA will be directly copied to the output waveform. So in this section for T5 and T3 we will have VCB. So T3 and T5 we have VCB. So in this section we have T1 and T5, so we will get VAB and the cycle will continue. So if you inspect the waveforms carefully, this will start at a lower value, it will reach its maximum and again go to that lower value, and this umbrella will continue. Since two thyristors are needed for circuit completion, we will not have any output before this point, because before this point there is only one thyristor conducting. So we will get a continuous output after the first cycle, or from the beginning of the second cycle. So you only need to draw from 0 to twice pi. So this diagram will be something like this. So if we want to draw the output wave shapes for alpha equal 30 degree, the whole triggering assembly will be shifted 30 degree forward. The rules will be same. So T1, T2, T3 will be 120 degree apart, and T1, T4, T2, T5, T3, T6 will be 180 degree apart, and the pulse will be repeated after every 60 degree. So again, if we analyze it, at this moment T4 and T2 is turned on, so we will get VBA. So we will have this flipped version of VAB. So look at the waveform at this moment. This waveform is decreasing from the maximum value. So the shape of VBA will start at its peak and will start to decline up until this point. After that, T4 and T3 will cause VCA, and after that T3 and T5 will cause VCB. But look at the wave shapes. These are not all the ways to 0, because at this moment the value of VAB is not 0. So you can complete the full cycle by analyzing these individual thyristors. But you need to draw the triggerings very carefully. If you get these triggerings wrong, you will get the output wrong. So you need to pay attention to the triggering sequence. So for alpha equals 60 degree, same thing will happen. The triggerings will be forwarded by another 30 degree, and in this point the value of VBA reaches 0. So again, here at this point VAB becomes 0, VAB becomes 0 here as well. So you need to pay attention to the shapes of the output waveform as well. So after that, at alpha equal 90 degree, the whole assembly of the triggers will be shifted again, and this time around we will have a discontinuity, because in this case, say VBA has gone to 0, but in this portion the current will become 0, so this will turn off T4 and T2. So again, at this moment T4 and T3 will continue as VCA, but VCA will reach 0 at this point. So there will be a discontinuity after alpha equal 60 degree. If you want to formulate the values for VDC and VRMS, the span of the waveform has now changed. So the span has become 2 blocks or 60 degree. So the T will be 1 by pi by 3. So pi by 3 means 60 degree. and the limits will be pi by 6 plus alpha to pi by 2 plus alpha. In this case, if we consider only the gridded portion, here alpha equals 0, so in this case the limit will be from 30 degree to 90 degree. So the limit, if we zoom in a little bit, the limit will be from 30 degree to 90 degree, and we need to determine the area under this curve. So same goes for VRMS as well. So these formulas can be found in the book. So these formulas are easy to derive, and this will become very helpful in doing maths. So if we go to our first math, this is a three-phase half-wave controlled rectifier where line-to-line voltage is 208 volt. The load is a resistive load which is 10 ohms. We need to find the output voltage and also calculate the RMS and average output current, average thyristor current, and rectification efficiency. So first off, we need to find the value of phase voltage. Since it isn't mentioned whether the voltage is line voltage or phase voltage, we have to consider it as line voltage. So to find out phase voltage, we need to divide it by √3, and to find the maximum voltage, multiply that value with √2. So if the value of alpha is provided, we must understand whether it is in continuous or discontinuous conduction mode. So in case of a three-phase half-wave converter, the discontinuity will start right after alpha is greater than 30. So in this case, this will be a discontinuous conduction mode. So we need to put these values in these formulas, which is elaborated in the book. So here only unknown values are Vm and alpha. So in this math, we have already got the values for Vm and alpha. So we can find the values of VDC and VRMS, and since it is a resistive load of 10 ohms, we can find the values of RMS and average output currents by dividing these values by 10 ohms. So far we have got output voltage, RMS, and average output currents. So the average currents of each thyristor will be the main current divided by 3. Since there are 3 thyristors and they will conduct for the same amount of time on an average, we can get the average current of each thyristor by dividing the DC value by 3. So here comes the rectification efficiency, which is PDC by PRMS. VDC IDC divided by VRMS, IRMS. So this math is pretty simple. For the second math, this is about a semi-converter which has the same specifications as our previous math. So in this case, alpha is provided 90°, which is a discontinuous conduction mode. So we need to put the values of alpha and Vm in these equations, which has been elaborated in these equations. So all we need to know is the value of Vm and alpha, so we can get VDC and VRMS. So once we get VDC and VRMS, we will have IRMS and IDC, since it is a resistive load. And again, to find out the average thyristor current, we need to divide the DC current by 3, since there are only 3 branches and this thyristor will conduct in conjunction. So for 3 branches we need to divide the current by 3 to get the average currents of each thyristor. So again, rectification efficiency is PDC by PRMS, so VDC IDC divided by VRMS IRMS. So the third math is for a full converter or full wave control rectifier with the same specifications as the previous maths. So if alpha is provided, we can find the values of IRMS, IDC, average current and rectification efficiency very easily for a full converter. So this ends our lectures on 3-phase control rectifiers.